Good day everyone. In today's lecture, we'll be discussing about the various power electronic converters circuits that we have. Then we'll be discussing about the various power electronic switches that we have. And we'll also be discussing about the various commutation techniques that are used in power electronic converters. And we'll be also be discussing about the phase control principle that we apply in a converter. And finally, we'll be classifying what all different type of converter circuits we have. We have different types of power electronic circuits. All the power electronic circuits we call it as converters. Now these converters can be classified into 5 types. The first type is called as phase controlled converters, or they are also called as rectifiers. It does nothing but it converts an AC quantity into a DC quantity. Now here we can see that the AC quantity is a constant quantity, while the output DC that we are getting, it can be a variable quantity. That is, I can increase or decrease the level of the output DC that I am getting. The second type of circuit we will be having, it is called as a chopper. Chopper is nothing but what it will do is it will convert a fixed DC input into a variable DC input. This means that I can increase or decrease the level of the DC output voltage that I am getting. The third type of circuit converter that we have, we call it as the inverters. Inverters does nothing but it converts a DC quantity into a variable AC quantity. Now here we can see that the AC quantity's output voltage can also be varied, that is the magnitude of the AC, it can be varied, and also the frequency, that is, for example, in 5 seconds if I am having one cycle, what I can do is I can increase this to 2 or I can increase this to half as well. That is, I can increase or decrease the frequency of the output voltage that I am having, and also I can change the voltage level of the output AC quantity. The fourth type of converter that I have, it is called as cycloconverters. Now in cycloconverters also, I'll be having a fixed AC. I'll be converting this into a DC, but the frequency of the DC will be changed. That is, for example, if I have 10 Hertz frequency, I can increase that to 50 Hertz or I can decrease that to 5 Hertz as well. What I will do is I'll be changing the frequency of the AC quantity that I am getting in the output. The fifth type of circuit that we have, we call it as AC voltage controllers, or it is also called as AC voltage regulators. Now here we can see that this also converts an AC quantity into a DC quantity. Here frequency of both these circuits will remain the same. That is, if I am having 10 Hertz frequency in the input, the same 10 Hertz frequency I will be having in the output as well, but the level of voltage will be changed. That is, the level of voltage will be increased or it will be decreased. So these are the 5 different type of power electronic converter circuits that we have. Now one important thing that is to be noted is that the inputs of each, let us classify the inputs of each and what is the output. Now looking here, we can see that in a converter I have the input to be AC, the output is DC. Then for a chopper, input is DC, output is DC. For inverter, input is DC, output I have AC, then AC to AC, same AC to AC. Now here we can see that the input quantities for 3 circuits is AC, while for 2 different type of converters it is DC. Now we have to keep this thing in mind, which all circuits have AC as input and which all circuits have DC as input, because we will be discussing this in the further lectures that we are going to see. In that we will be discussing this. Now moving further. Now whenever a power electronic converter is implemented, some switches will be using. Now this switch can be a diode, or it can be an SCR, or it can be any other different type of switch. Now these switches can be classified into various categories. The first category is uncontrolled turn on and uncontrolled turn off. That is, for example, if this is the output that if this is the input AC wave that I am having, Uncontrolled turn on means that is it will start conducting at 0 and it will conduct up to pi. That is, I cannot vary anything. That is, once my device becomes forward bias, directly when it becomes forward bias it will start conducting, and when it is becoming reverse bias it will stop conducting. That is, turn on also cannot be controlled as well as turn off cannot be controlled. The circuit is turning off because the supply is becoming reverse bias. So this is the first category of switch. We call it as uncontrolled turn on, uncontrolled turn off. That is, when the supply becomes forward bias, the switch directly turns on, and when the supply becomes reverse bias, the switch directly turns off. That is, if the direction of current is reversed, it will directly turn off. The second category of switch that I have, it is called as controlled turn on and uncontrolled turn off. That is, I can decide when it is going to turn on, but I cannot decide when it is going to turn off. Now, for example, that this instant I will be calling as 0, this I will be calling it as pi. Now, for example, I can decide that is at pi by 4 my switch will turn on. I can decide when my switch is turning on, but it will conduct up to pi. That is, only the turn on time I can decide. Now this type of switch I call it as the controlled turn on and uncontrolled turn off switch. Now the SCR falls in this category. SCR, triac, all these type of devices, this falls in this category. That is, once the supply becomes reverse bias, it will directly turn on. But when the supply was forward bias, it didn't start conducting. So when I am giving a firing impulse, only from that instant it will start conducting. Let me call the firing pulse angle to be alpha. From alpha to pi it will conduct. The third category of switch that I have, we call it as controlled turn on and controlled turn off. Now, in the first category, from 0 to pi, it was conducting. In the second category, we saw that from alpha to pi, it was conducting. From alpha to pi, it was conducting. Now, the third category of switch that we have, in this we can see that I can control the turn on time as well as I can decide when it will turn off. That is, from alpha to beta, I can decide when it will turn on and I can also decide when it will get turned off. Both these are in my hands. That is, once my supply becomes forward bias, I can decide when it is turning on. Before my supply becomes reverse bias, before that instant I can also turn off my device. So this is the third category of device we have. Now in this, power BJT, power MOSFET, IGBT, all these comes under the third category of switch. So this also has to be kept in mind, because based on this only we are getting different converter circuits. All the 5 converter circuits that we are going to discuss, it will be based on the classification of these switches, and the most widely used switch will be SCR. It is not necessary that only SCR can be used. Power BJT can be used, power MOSFET can be used, IGBT can be used. This SCR can be replaced by any type of switch that we have in power electronics. Then the next technique that we have is commutation. Commutation is nothing but turning off an SCR is called as commutation, or turning off a thyristor, we call it as commutation. Now this commutation can be achieved using 2 techniques. The first technique is called as natural commutation. In natural commutation, no external circuitry is required. And the second technique that I have talked about is forced commutation. The forced commutation, it requires some commutating element. So this forced commutation will be dealt with in detail in the upcoming lectures. Then let us discuss what is natural commutation. For example, if I am having an AC signal, now this is AC signal. If I am having a device, what this device will do? This device will get turned on. This is forward bias. That is, in the first half cycle, my device is forward bias because plus and minus will be in this manner. In the second half, it will be reverse bias. Reverse bias means this polarity will change. This will become minus plus. So in this instant, my switch will be off. Now what will happen is, as I am having an AC supply reverses itself. So it means that after some fixed time or after some fixed duration, I will get a cycle where my device is going to get reverse bias. Now for this reverse bias, what will happen? My switch, it will directly turn off. Here it will conduct. It will be on in this duration, that is depending on when I am giving the gate pulse. This will be on in the positive half. It will be off in the negative half. So because this is the characteristics of AC, it will have a positive cycle and it will have a negative cycle. So when we are going for the negative cycle, the device will become reverse bias and it will directly turn off. So this type of commutation, we call it as natural commutation, or the other name for that is line commutation. We can call it as natural commutation or line commutation. This is because of the characteristics of supply. So if I am using an AC supply, I can get natural commutation or line commutation. So as AC supply already we have, no external circuit is required, because AC supply itself reverse biases the device and it will make the device to be turned off. The second type of commutation that I am having is called as forced commutation. Now in forced commutation, if for example if I am giving a DC supply, now in DC supply what happens? This is forward biased. For the entire duration the device will remain forward biased. So what will happen? Now when I am giving a firing pulse here, from here I will start getting the output up to end, that is till when my DC supply is given, till that time my device will conduct. So there is no stopping my device from conduction. That is, if I want to turn off my device, what I'll have to do is I'll have to turn off this supply. So if I'm turning off this supply, that is not a desirable characteristics in any of this circuit. So here we can see that now what I have to do is, for example, if the current was flowing in this direction, I have to reverse the direction of current. Now for reversing the direction of current, some external mechanism or some additional elements has to be added. For example, like an inductor, like a capacitor, or an auxiliary thyristor. Some element has to be added. Now these elements, what it will do is it will help in reversing the direction of current. So based on this, my thyristor will get turned off. Now as we have said earlier, now here we can see that for converter, phase control converter, the input is AC. For chopper, input is DC. For inverter, input is DC. Cycloconverter is AC. For AC voltage controller is AC. So here we can see that for phase controlled converter, for cyclo converter, and for AC voltage controller, I will get natural commutation. Why I will get natural commutation? Because my input supply is AC and no external circuitry is required to turn off my SCR. So for these three type of circuits, I will directly get natural commutation. And for circuits like chopper and inverter, I cannot get natural commutation. So I'll have to go for forced commutation in these two type of circuits. Why? Because the input supply that I am giving is DC and my SCR will not turn on. So for turning off my SCR, what I'll have to do is I'll have to go for forced commutation. Now this forced commutation, it has some 5 different type of techniques are there in forced commutation. We'll be discussing about this in the upcoming lectures. The next principle that we are going to discuss about is phase control. Now phase control is nothing but, this is the very basic guiding principle of a converter. Now for understanding phase control, let us start with the diode. Now in diode, as we have seen, there are 3 different type of switches. So diode came under the first category. The first category was uncontrolled turn on and uncontrolled turn off. So diode was in the first category, that is turn on is also uncontrolled, turn off is also uncontrolled. So we can see here that for a diode I have uncontrolled output. So this is clearly understood based on the classification of switches that we had. Now this is the AC supply that is given. So in the AC supply, we know that if I am connecting a diode, what will happen? In the positive cycle, diode will become forward biased. In the negative cycle, it will become reverse biased. So this is clearly understood of a diode. In negative cycle, diode will have a polarity minus plus. in this manner. So it will become reverse bias. In positive, in forward bias or in positive cycle, it will have polarity in this manner. So the diode will conduct. So from we know that the output of a diode will be something in this manner. So we can clearly see that in the positive half cycle diode is conducting, and in the negative half cycle diode is turning off. That is, this I am not getting. This is for if I am using only one diode. So if I am using two diodes, I can replicate, that is, I can get this operation as well. But here I am using only one diode. So when I am using one diode, in for forward bias my diode will turn on, in reverse bias my diode will turn off. So this is turning off duration and this is turning on duration. So we can see that from 0 to pi there is full conduction, that is full half waveform I am getting. From 2 pi to 3 pi also I am getting the full half waveform, and from pi to 2 pi as it is off, I am not getting any waveform, that is there is no waveform present over in the negative half cycle. So this is clearly understood, I think. Now based on this, let us look into how an SCR will operate. So SCR, it fell under the second category. The second category was controlled turn on and uncontrolled turn off. That is, I can decide depending on when I am giving the firing pulse, it will turn on. The SCR will operate almost similar to a diode, but only one change is here, that here I am having a gate. That is, when I am giving a gate signal, depending on that gate signal, it will start conduction. So this is my AC supply. So this is the forward bias duration, the positive half, the negative half is the reverse bias. Now what happens is, in the forward bias my SCR will have some signal like this, in the reverse bias it will have some opposite polarity. Now depending on when I am giving the gate signal, that is, I have to give a positive gate signal. So when I am giving the positive gate signal, depending on, that is, forward bias also has to be there and a positive gate signal also has to be there. When these two conditions are satisfied, my device will start conducting. Now here we can see that at alpha, at this duration, I am giving a gate pulse, that is a positive gate pulse I am giving. At 0, my SCR at 0, it is forward bias, but it is not conducting. When it will start conducting? It will start conducting when I am giving a positive gate pulse. So positive gate pulse is given at alpha. So from alpha to pi, we can see that I am getting an output I am getting. But the dotted lines, this portion shows that I am not having any output from 0 to alpha. There is no output. Only output I am getting in the duration alpha to pi duration, I am getting some outputs I am getting. So this is clearly understood, I think. And in the reverse bias duration also we can see that there is no conduction. Why? Because of natural commutation. Why natural commutation? Because I am using an AC supply here. In AC supply, in the second half, the supply directly reverses itself, and because of that I am having natural commutation, and here there will be no conduction. Again we can see here that at 2 pi my SCR, it will become forward bias, but it will not conduct, that is, it has not turned on. When it will turn on? It will turn on at 2 pi plus alpha, that is, at alpha I am giving the firing pulse, that is 2 pi plus alpha duration, my SCR will turn on. And we can clearly see here that from 2 pi plus alpha to 3 pi my SCR will conduct. That is, only during this duration my SCR is on. The dotted lines that are shown here, it shows that here I am not getting any output, and from 2 pi plus alpha to 3 pi I am getting an output, and from 3 pi to 4 pi there is no output, because this is reverse bias in this duration. So for getting a controlled output, what is required? Forward bias is also required, as well as a gate pulse is also required. And this principle that we have discussed over here, this is called as phase control. So using the principle of phase control, we can implement power electronic circuits, we can implement. So it is clearly understood that, so that is why this AC to DC conversion that I am talking about, we'll be calling it as rectifier. This circuit can also be called as a rectifier, or it is called as a phase controlled converter. So that is why we'll be referring to it as converter, or we'll be referring to as rectifier. Converter is nothing but phase controlled converter. So this is the basic principle of phase control. Phase control is nothing but based on when I am giving the firing pulse, from that instant I'll start getting the output till the end of forward bias. So this is the very basic principle of phase control. Now we'll discuss about the classification of a phase control converter. Now this is how a phase control converter is named. For example, single phase full wave controlled converter with R load. Now let us see what all different type of circuits are possible. The first phrase that is in this in the name of this converter is single phase. Now we know that a converter is a device which converts AC to DC, and in AC we know that we have two different type of supplies, that is a single phase and a three phase. So from the name it is clear that this single phase can also be replaced with three phase. Then we have full wave. Now full wave, we know that when we have already studied about diode rectifiers. Now in that we know that we have two different type of circuits that are possible, that is a full wave rectifier and a half wave rectifier. So this full wave, it can be replaced with half wave as well. We also know that when I am talking about full wave, in full wave I have a bridge configuration and I have a midpoint configuration. So in the second phrase, that is full wave, this can be replaced with full wave bridge configuration or full wave midpoint configuration or half wave configuration. So the first phrase, it was single phase. In single phase we have single phase or three phase, it can be replaced. The full wave, it can be replaced as full wave bridge configuration or full wave midpoint configuration or half wave configuration. The next is controlled. Now as we were classifying the switches, we saw different categories. We saw that is uncontrolled, controlled, the different categories of switches we saw. So here this control term, it can be replaced with uncontrolled. Uncontrolled means nothing but if I am using diodes in this converter, I call it as uncontrolled. Controlled, that is if I am using a controllable switch like SCR, IGBT, power MOSFET, power BJT, GTO, etc. I'll be calling it as controlled. Then we have one more category that is called as semi-controlled. Semi-controlled is nothing but I'll be using diodes and SCRs in combination. So I can call it as half controlled. That is, I have controlled means I have fully controlled, I have half controlled, and I have uncontrolled. So this controlled term, it can be replaced with uncontrolled, fully controlled, half controlled. So controlled, it generally it indicates fully controlled. Then we have converter. So converter, we cannot do anything with about this converter. Then we have the load part. In the load part, this is R load. Then we have RL load, then we have RLE load. That is, RL load is nothing but a resistor and an inductor connected in series. R load is nothing but a resistive type of load. RLE load is nothing but a resistor, an inductor, and a battery connected in series. So these are the different type of configurations possible for a converter. Now let us see for an example. Now for example, the name can be three phase half wave fully controlled converter with R load. So this clearly indicates that the supply given is three phase. Then we have half wave. Only we are discussing about half wave, that is only positive cycles. I'll be controlling only the positive cycles. Then I have fully controlled. Fully controlled means all the devices that I have are all SCRs. Then I have converter with R load. R load nothing but resistive load. Now let us look into another example. Another example is single phase full wave bridge fully controlled converter. Fully controlled converter means what? The supply given is single phase AC. I am concerned about the two halves, the positive half and the negative half. The configuration that I am going to use is bridge configuration. Bridge configuration, we know that this is the bridge configuration. I am using bridge configuration. I am concerned about the bridge configuration. Then I am using I said full control. Full control means all the devices in the bridge configuration are SCR. So in this manner we have different configurations possible for my converter. So in supply I have two different configurations, single phase or three phase. In full wave I have full wave or half wave. So here also I have three, that is full wave bridge, full wave midpoint and half wave. In controlled I have fully controlled, semi converter, full converter and fully controlled, uncontrolled and half controlled. Then R load I have three different type of load. So we can understand how many different type of circuits are clearly possible when I am talking about a phase controlled converter.